Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video to those that need it. In today's class, I want to present to us everything we need to know about simple AC circuits in a summarized form. I have done a lot of video series on this topic and this is just to cap it up. Endeavor to click in the description below and you will find all the video series on this topic. The reason why I'm making this video is because a lot of students are confused and they don't know what to do in this topic. If you are able to go through this video, you are going to get mastery knowledge on this topic. And there is no question that will be set that you will not have the mental power to answer. Without wasting much time, let us go straight to the business of the day. First off, I want us to look at the A part of this class, general knowledge on simple AC circuits. Examiners may ask you to calculate the instantaneous current, and this is the instantaneous current number 1 here. I as a function of t. They will also ask you to calculate the peak or the maximum current. It is represented with an I naught, and the examiners may also ask you to write down the equation that relate the instantaneous current and the maximum current. And this is that equation. This is the equation here. We also have instantaneous voltage represented with a V subscript T, V as a function of T. We also have the peak or maximum voltage, and this is the equation that relates the peak, the instantaneous voltage and the maximum voltage. We are going to explain everything as we move down. And here we also have the Ohm's law. The Ohm's law is a very important equation in this topic because we're dealing with electricity, and this equation is customized to fit into all the equations here. We also have the root mean square current represented with this equation. Next up, we have the root mean square voltage represented with this equation. We have the angular frequency or angular velocity, which represented with omega. We have the phase angle. You know that omega also means omega is equals to 2 pi f. We also have the phase angle. The phase angle is represented with omega and a t. And then we also have the phase difference. We also have the current and the voltage vibrating out of phase. They may ask you to explain the meaning of the current and the voltage vibrating out of phase. When current and voltage vibrate out of phase, we mean they vibrate with different frequencies and different velocities. It also means that the current and the voltage reach their peak, their zeros and their minimum values at different time interval. All these are explained in the videos that I have produced on this channel. They will ask you to also explain why the current and voltage being in phase. When the current and the voltage are out of phase, the phase difference is equals to 90 degrees, is equals to 90 degrees or pi all over 2. That is what happens. So when they are in phase, when the current and the voltage are in phase, it means that they vibrate with the same frequency, the same velocity, and they reach their peak, their zeros and their minimum at the same time. In that case, the phase difference will be equal to 0, not 90 degrees or pi over 2 by this time. Next up, current or voltage lead. Yeah, current or voltage may lead, and this can only take place when the current and the voltage are out of phase. So one taking the lead. If current is leading, the current will reach its peak, its 0 and minimum, before the voltage will reach its peak, its 0 and minimum, and vice versa. And the current will lead by pi. The current or the voltage may lead by 90 degrees or pi all over 2. These are the basic information that you need to know here. Similarly, the voltage or the current lagging, it is just like two athletes are running, and one athlete reach the finish line 5 minutes earlier. So we say that the athlete leads the race by 5 minutes. So the other athlete is arriving 5 minutes later. So the athlete that arrived 5 minutes later lags the race by 5 minutes. That is just that. They will ask you to calculate the power in the circuit. And the power in the circuit is simply P is equal to IV, the normal power you know in current, and cos phi is the power factor. So this is the power factor where you make phi the subject formula, whatever you find becomes the power factor. Examiners may ask you to calculate the resonance frequency. This is the symbol for the resonance frequency. There are so many conditions that leads to resonance in simple AC circuits. One of them is that when the capacitive reactance is equals to the inductive reactance, XL is equals to XC. That will give us this particular equation here. So we have looked at the general knowledge. At this point, I would like us to look at separate circuits. This B part of this lecture is talking about a pure resistor circuit. What are those things that you need to know about a pure resistor AC circuit? This is the circuit. These arrows are not supposed to be here. Reason being that in simple AC circuit or in AC, there are no polarities. The current can decide to flow in any direction. We only have direction of flow of current in DC circuits. This is the error in this diagram. You bear with me. Thank you. So note the following in this type of circuits. Number one, what I just projected right now is very, very important. You need to know that for a pure resistor circuit, what happens to the alternating current and the alternating voltage is very, very important. So when a resistor R is connected in an AC circuit as shown above, it makes the alternating currents that IR as a function of T and the alternating voltage VR as a function of T to vibrate or oscillate and be in phase. I have already explained the meaning of in phase and out of phase in the previous slides. So that is both the current and the voltage reaches their peak or maximum 0 and minimum values at the same time. It also means that the voltage and the current vibrate with the same velocity and frequency. By this, the phase difference phi is 0. I said all that before. The resistor in the circuit also opposes the flow. This is a typo error, a flow of AC. And this opposition to the flow of AC offered by, this is a typo please, flow of AC offered by a resistor is called resistance. So this is the basic information that you need to know in this circuit. Examiners love asking questions around this. The next thing that examiners may ask you to do is to draw the circuit diagram. This is the circuit diagram as projected before. There are no polarities. Next up, the examiners may ask you to draw the sinusoidal waveform for a pure AC circuit. And this is how it goes. Here, the blue line stands for the voltage, and then the purple line stands for the currents. They are vibrating in phase. You see them going this way and coming this way. Up here is the peak. Here is the zero values. Up here are the peak values, and down here are the zero values, and down here and here are the minimum values. So you can see that all of them are reaching these places at the same time. And from here down to this place is pi all over 2, and from here to here is so from this line to this line gives you one complete circle, and that one complete circle is the same thing as 2 pi in radians. And then here is the period t. The period for one complete oscillation is this length of the line, which is equal to 1 over f. And here is the theta, and here is the theta and the angular velocity. That is what you have here. Next up, the examiners may ask you to draw the phasor or the vector diagram. Very, very important. And this is the phasor or the vector diagram. Here is angular frequency, not written in bold letters. And here is the current IR and then VR. So you see the arrows facing in one direction, meaning they are all in phase. Next up, they may ask you to find the phase difference. The phase difference in this particular circuit is always equal to 0, as you can see it here. A pure resistor AC equation is what you just see here right now. Because the phase difference is 0, this equation, I as a function of t equals to Im sine theta into omega t plus negative phi. So since phi is equal to 0, the equation will shrink to this form. And this is a pure resistor AV alternating voltage equation. This is it here. They will ask you to calculate the resistance in the circuit. Ohm's law equation is also very, very important here. The Ohm's law equation is customized to fit into such equation. A power in pure RAC circuit. They may ask you to calculate the power, and for this particular type of circuits, the power is given to be IV or I square R. Next up, we want to look at a pure capacitor AC circuit. You see the way I arrange this stuff. We look at the general knowledge, a pure resistor circuit, a pure capacitor circuit, as you can see here. So for this circuit, what do you need to know? Summarize here. When a capacitor C is connected in an AC circuit, as shown above, it makes the alternating current and the alternating voltage to vibrate or oscillate and be in different phase. They are out of phase, hence making the current to lead by 90 degrees or pi over 2 radians, and the voltage to lag by 90 degrees or pi over 2 radians. That is, the current and the voltage reaches their peak, maximum 0 and minimum values at different time. It also means that the current and the voltage vibrate with different velocities and frequencies. By this, the phase difference phi is equal to 90 degrees or pi over 2. Also, the capacitor is a device that stores electric charge. But for this type of circuit, the capacitor also opposes the flow of alternating current, and this opposition to the flow of alternating current offered by a capacitor is called the capacitive reactance. This is a summarized knowledge, what you need to know about a pure capacitor AC circuit, summarized here for you. Next up, they may ask you to draw the circuit, which I drew before. This is it here. The examiners may ask you to draw the sinusoidal waveform for a pure capacitor. This is not R, for a pure capacitor. And this is the sinusoidal waveform. They are out of phase. In this, the purple line is leading. So it means that in this circuit, the current leads and the voltage lag. The current reaches its maximum here before the voltage is reaching its maximum. This is it. The current reaches its zero values here before the voltage is reaching its zero value here. And so in each, the current is arriving at that place before the voltage. So the voltage is lagging by 90 degrees or power 2. Examiners may ask you to calculate to draw the phasor diagram. And one thing I want to tell you guys is that the one that is leading, this arrow will face that direction, as you can see here. This diagram can be drawn like this. We can equally draw this diagram like this. And our IC will be here, and our VC will be here. And then you can draw it this way. So it is not a must that you draw it the way it is appearing here. You can equally draw it this way. Good. The current is leading by pi over 2 or 90 degrees, while the voltage is lagging by pi over 2 or 90 degrees. Next up, the examiners may ask you to give the phase difference. A pure capacitor AC equation, this is it here. The capacitance of the capacitor will also be required, and this is the equation for it. Q, this Q here is the quantity of electric charge, Q, and it's given to be equal to IT. Q is equal to IT. So these are the stuff that you need to know here. So we can equally write this equation as C is equal to IT all over V. It is T, another equation. And then the capacitive reactance. The capacitive reactance is given to be this, and you know that XC can also be written as 1 all over. You know that omega is equals to 2 pi f, and so we can write this equation as 2 pi fc. This particular equation can be written as this again. So these are the stuff that you need to know that will help you to survive in this topic. Next up, the Ohm's law equation, which was written to be V is equals to IR, is now customized into V is equals to IXC, meaning the capacitive reactance and the resistor, they are measured in the same unit of ohms, since both of them does the work of opposing the flow of currents. So this is the customized Ohm's law equation. Next up, they may ask you to calculate the power, and for the power, these are the two equations that you may use. The power P is equal to IV, the current times the voltage. The power is also equal to I square, in place of I square R, P is equal to I square R. So in place of I square R, this R is now serving as this. So we can now replace that with that. So right now we want to look at a pure inductor AC circuit. For a pure inductor AC circuit, this is the circuit diagram, and this is all that you need to know about the pure inductor AC circuits. Here, the currents and the voltage are also out of phase, but in this case, the voltage will lead and the current will lag. Also, the inductance of the inductor will be calculated, and also the inductor coil also does the work of opposing the flow of AC currents, and that opposition to the flow of AC current is called the inductive reactance, or the reactance of the inductor XL. So these are the basic things that you need to know in this particular circuit, and you also need to know how to draw the circuit diagram. This is the symbol for the inductor coil. The arrows can face any direction. Next up, the sinusoidal waveform for a pure L. L stands for inductor, and then this is it. In this case, I said the voltage will lead, and as you can see here, the voltage is leading. Its peak here before the current is attaining its peak at this point. The voltage also first attains its first zero value here before the current is attaining its zero value here. So we can say that the voltage is leading by this pi all over 2 or 90 degrees, and then the current is also lagging by pi over 2 or 90 degrees. The phasor of the vector diagram for a pure inductor AC circuit, and this is it. As I said earlier, it is not a must that you draw this like this. Here is your, this is your VL, and here is your, this is your IL, this is your IL. So this and here is your omega, angular frequency or angular velocity. So this diagram can also be drawn like this. We can equally draw this like this. This is our IL, and this is our VL. So this is, so since the voltage is leading, we can put the arrow to face this way, and this is our omega, or angular frequency. You can equally draw it in such a way that this IL will be vertical and then VL will be at the horizontal, but the arrow will still face this side. That's just the only thing that you got to do here. So we also have this, examiners may ask you to phase difference, to state the phase difference for this type of circuits. The phase difference is this. Also, the pure inductor, the equation, this is the equation, the alternating current equation, the voltage equation, and here is the equation for the inductance of the inductor. L is equal to mu n square over A divided by I, or L is equal to phi n over I. Then next up we have the inductive reactance XL. It is given as omega C, omega L, and this XL can also be written as 2 pi FL, and that is also fine. So you can apply the physics of Cot and John here and get more equations here. And this is the customized Ohm's law equation. We said our V is equals to IR, and in this case our R is serving as the XL, because both of these guys, they are measured in the unit of ohm, because they all oppose the flow of currents. The power, this is the equation for the power. P is equal to IV and P is equal to I square L XL. Next up, we are done with the single circuit. At this point, we want to look at the E part of this lecture: series, resistor, and capacitor AC circuits. This is what you have. As I said earlier, there are no polarities here. You can remove this polarity, but this is how the circuit looks like. Now, one thing you got to know here is that the behavior of resistors in series, you apply the same sense here. The resistors are in series, the same current flows through them, and this is exactly what you're gonna have here. So this is it. You go through this, and then you are fine. This is the summary of everything that you got to know in this circuit. Next up, we they will ask you to draw the circuit diagram, and this is the circuit diagram, no polarities. The vector of the phasor diagram, this is it. This is the vector of the phasor diagram. The diagrams are explained in the video I have done on this topic. You may fall back to them and get more clarification. Just click in the description below and you will see that I just did this video to bring our attention to the things that we must know, the areas of concentration where we must pay attention, and these are the stuff that you must pay attention to. Next up, you have the phase difference here. The phase difference here is calculated like this. This is a calculation here. They are all explained in that video. But while watching a video, you watch out for places like this. When you see this stuff, you have to pause the video and get it done. Because if any examiner wants to set you questions, they will touch any of this stuff that I'm showing you guys here today. So a series resistor and a capacitor is the equation that is it here. And then the resistance, they may actually calculate the resistance, the capacitance, the capacitive reactance. Next up, you have the impedance. There's the presence of impedance here because you have the resistor and the capacitive reactance in place, and that gives us the impedance, the overall opposition to the flow of current offered by a resistor, a capacitor, an inductor, or both of them. So this is it, the power factor. The power factor is calculated as this. And you can use this diagram here to generate all the equations. Just applying Pythagoras theory. They are all explained in that video that I asked you to go and watch. And so you have the impedance, the power factor, the resistance, and you can replace your Z here with root R squared plus XC squared. Ohm's law is customized, and these are the customized Ohm's law equations that you will have here. This one for the resistor, this one for the capacitive reactance, and this one for the overall opposition to the flow of current caused by this and caused by this. Then you also have the power for a series resistor and capacitor AC. You have the power as given as IV cos phi and also I square Z. This case not I square R or I square XC, but I square Z. That is it. Next up, we want to look at a series resistor and inductor circuit. This is how the circuit looks like. No polarities, take note. And this is the summary of everything you need to know about the circuit. Everything. You grab it and then you are good to go. Next up, examiners may ask you to find the circuit diagram. To draw the circuit diagram, and this is it, as I showed you earlier, no polarity. The phasor or the vector diagram for a series resistor and inductor circuit, this is it here. This phasor diagram is very, very important. You can decide to use this phasor diagram here to generate all the equations. I explained that in the video series. For instance, you can decide to name this as triangle. Okay, let's call this OBA triangle OBA. You can detach this and apply Pythagoras theory and you are fine. Knowing that here is your VR and up here is also your VR, and this side are your VL. You apply Pythagoras theory and find all the equations needed here. Next up, the phasor, the phase difference tanϕ for a series resistor and inductor AC circuits. This is it. This is it here. Equations for the voltage, for the current, the equations for the inductance L. You have inductive reactance omega L. This time we don't have xc square here, but xl square. You also have Ohm's law customized. This is for the R, this is for the XL, and this is for the entire resistance in the circuit Z here. This and this can be used to calculate the power in the circuit, where cos phi only stands for the power factor. And in this case, cos phi here is equal to the R all over Z. This is it here. So next up, which I suppose is last but not the least, is a series circuit containing R, L, and C. This is the circuit diagram. Your resistor, your inductor, your capacitor. And here, if you can permit me to write, here is your R, here is your XL, here is your XC. So these are resistors in series. So we're going to have the same current flowing through here. The same current flowing through here. Or in this direction. Good. So this is a summary of all that you need to know in this circuit here. Copy it down your notebook and you'll be fine. This is it. This is the summary of everything you need to know in this particular circuit diagram. And next up, examiners may ask you to draw the circuit diagram, and this is it. No polarities involved. And the vector or the phasor diagram, this is it. As I told you before, you can apply Pythagoras theory here and summarize all the equations. And for the phasor, for the phase difference, this is how to go about it. This can be gotten from the diagram I just showed us here. And for the current, this is what you have. For the voltage, this is what you have. The resistor, they will ask to find the resistance of the resistor, the inductance of the inductor. The capacitance of the capacitor. Remember I told you what Q is, the inductance of the inductor XL. That is to say, all that we have done with the single or pure circuit or total circuit are all combined here in one place. And this is the capacitance of the capacitor. This is it here. The effective reactance. Here we talk about reactance. Reactance is the overall opposition to the flow of current offered by an inductor or a capacitor. So reactance comes in when you have, this is the effective reactance, the XL minus the XC. The XL minus XC because the voltage is leading and this is lagging here. And that is why we're having this here. And then the impedance. So that the impedance has a longer equation here. This is it here. The overall opposition to the flow of AC offered by a resistor an inductor, a capacitor, or both of them. So since XL minus XC is equal to this, we are free to say that R squared plus X squared. For the Ohm's law customized equations, these are the equations that you have here. For the resistor, for the capacitor, for the inductor, and then for the entire resistance in the circuit. That for the power, this is what you have, this or this. And then for the power factor, this is what you have. This was mentioned earlier. It's a typo. And then in this circuit, you'll be asked to calculate the resonance frequency. I told us when resonance occur. When resonance occur in simple AC circuit when XL is equals to XC. That is when omega L is equals to 1 all over omega C. That is when resonance occurs. So you change your omega equals to 2 pi f, and you substitute and you change your f to equals to f naught, and then you make f naught the subject of the formula, and then you find this particular equation here. So conditions for resonance to occur in simple AC circuit, I gave us some conditions. We have to research and find more of the conditions. So they may ask you to also state the application of resonance. Advantages of AC over DC for power transmission. Thank you, and God bless you. Don't forget to subscribe, like, comment, and share. This is all that you need to know about simple AC circuits. I wish you success in your internal and external examinations. God bless you.